Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So today what we're going to be talking about is section 6.2, where we will be dealing with systems that are either linear or what we will call almost linear. Linear and almost linear. Systems. Alright, so this is building on what we were talking about before by way of classifying what happens when we investigate the origin in a linear system of differential equations. And here's the basic idea. So if 0, 0 is the critical point of a linear system, and in particular it's going to have some form like x prime equals ax plus by, and then y prime is going to equal cx plus dy. So if 0, 0 is the critical point of a linear system such as this, and we have eigenvalue lambda, eigenvector v, the basic ingredients of solutions will generically have the form E lambda V. And what this means is that, E lambda T V. And then what this means is that this part right here, which is basically acting like the weight on the vector, is going to be experiencing the effects of either exponential growth or exponential decay, depending on the nature of the lambda. So that means the solution curves will be pushed along the eigenvectors with either exponentially growing or exponentially decaying weights. Growing or decaying weights. Depending on lambda. So in particular, the more lambda is positive, the more it's going to be pushing out along V. The more lambda is negative, the more it's going to be tending to collapse away from the vector V. So in particular, if lambda is greater than 0, the solutions point outward origin in the direction of v if lambda is less than 0, the solutions do the opposite. They point inward towards the origin, in the direction of v. And if lambda equals 0, then what we end up with is a case where the weights are not actually changing, and so paths will just be following in the direction of v, but not ever more so or ever less so. So this means that the weight on v is constant, causing just basically a translation of a line, so causing a translation of solution curves in the direction of v, making parallel lines. Now if lambda is real and repeated, then the weights will be equal, but the directions may be a little weird. So if A, which is the matrix made of these coefficients, A, B, C, and D, is complete, as in not defective, in other words, with two linearly independent eigenvectors, we get either a proper nodal source, that's if lambda is positive, a proper nodal sink, that's if lambda is negative, or parallel lines if lambda equals 0. It's kind of a weird special case, but just it's in there. So these are also sometimes called star points. And they always look like this. Okay, so anyway, so there's that. Now, if on the other hand A is defective, we get an improper sink if lambda is greater than 0, or source. Sorry, that's if sink is if lambda is less than 0, or source if lambda is greater than 0. Of the form and then here what we'll have is some line, and then all of the solutions are going to be spiraling, not spiraling exactly, but they're all going to end up parallel to some other So it doesn't quite complete a spiral, but nonetheless it looks kind of spirally. And so sometimes this is called a spiral point. Even though it doesn't actually produce a full-on spiraling orbit. To get an actual spiraling orbit that goes all the way around, that requires a complex solution. So note, the solutions never complete a full rotation, just as a critically damped oscillator never completes a full oscillation. Okay, then, and it's a sink or source, so it goes into or out of the origin that way. And then if lambda is complex, then that's when you get a legitimate spiral. So a legitimate spiral sink or spiral source, as opposed to just these spiral points, comes from the case where lambda is complex. So if lambda is complex, then lambda equals alpha plus beta I. Alpha is equal to the real part of lambda. Then if the real part of lambda is greater than 0, what we have is a spiral source, and these are true sources in the sense that They go around like that. Or maybe it's more elliptical. And if the real part of lambda is less than 0, we have a spiral sink. And notice these do complete full rotations. Unlike what are called spiral points, which don't. Okay. And then if the real part of lambda is 0, what we get is a center which is stable but not asymptotically. But not asymptotically stable. So those look like just a bunch of concentric circles or ellipses. Now note, the reason we're so interested in this classification scheme is not the narrow context in which we first developed it, but a broader one. So we can extend this classification scheme to a broader context. So in particular, here's how. So the tool that we'll use is what's called the Jacobian matrix. So the setup for this, we're going to say x prime is equal to f of x sub y, so a function of x and a function of y. Y prime is equal to g of x sub y, so a function of x and a function of y. And then some notation. If you've taken Math 254, you know this. If not, you may not. So notation, f sub x represents the partial derivative of f with respect to x. So in other words, you treat y temporarily like it's just a constant. Treat y as a constant. F sub y, g sub x, and g sub y are defined similarly. Or say analogously. So then J, the Jacobian matrix, is equal to the matrix that you get when you plug in, or when you put in f sub x, f sub y, g sub x, g sub y. Then, if x 0 sub y 0 is a critical point, we can determine whether it's let's see whether it is an isolated critical point by taking the determinant of j of x naught y naught. So the Jacobian determinant at that one particular point, taking the determinant of, or in the determinant of that, and confirming that it isn't 0. Now, okay, so we can take the Jacobian determinant at a critical point and figure out if it is going to equal 0 or not. And if not, then, assuming that the functions are continuous enough, then we actually can linearize the function and produce an almost linear system. So, if x naught comma y naught is an isolated critical point, so remember, critical point means that x prime equals 0, y prime equals 0. And isolated means the Jacobian also at that point is not equal to, the determinant of the Jacobian is not equal to 0. So then if f and g are sufficiently differentiable at that point, we can call it almost linear, and characterize the equilibrium through the eigenvalues and eigenvectors of j at that point, x naught, y naught. So the eigenvalues and eigenvectors of Jx naught y naught according to the same criteria as we use for linear systems at the origin. Okay. So this is it's a lot of words, and it's hard to know. Does it even make sense? Who even knows? Let's just dive into some examples, because that's the only way to make heads or tails of this. And so here's what we do. So here's a process. It's a process. And this is for classifying equilibrium points. Alright, so here's what the setup will be. We'll have x prime is equal to f, x comma y, y prime will equal g, x comma y. So step 1, find the critical points. By setting f equals 0, g equals 0, and solving. Okay, so this is a thing we already know how to do. Secondly, calculate j of x naught, y naught for each critical point. X naught, y naught. Okay, so each critical point, calculate the Jacobian matrix. And then 3. Confirm that the determinant of j, x naught, y naught is not equal to 0, confirming that it is in fact an isolated critical point. So, i.e., x naught, y naught is isolated. 4. Find the eigenvalues and eigenvectors if appropriate, namely if we don't have to do anything weird in the way of complex eigenvalues or generalized eigenvectors, things like that. Eigenvectors of the matrix. Jx naught, y naught. And then use these to classify. X naught, y naught. So let's just try this and see, is it easy, is it hard? So to start with, we'll take an example where what we have are only constant terms disrupting the linear nature of the system that we're talking about. So x prime equals x minus 2y minus 8. X prime equals x minus 2y minus 8. And y prime is equal to x plus 4y plus 10. Okay, step one, we have to find the critical points. So 0 equals x minus 2y minus 8 would imply, for one thing, that x equals 2y plus 8. Just moving things over. And then 0 equals x plus 4y plus 10, so that would be the y side of things. I can just put that into play up here and get 0 equals 2y plus 8 plus 4y plus 10. 0 equals then 6y plus 18. So move that over, divide, and that would mean y equals negative 3. And then up here, putting that in, 2 times negative 3 is negative 6. Plus 8 would imply that x equals 2. So then, just quick confirmation, 2 minus negative 6 plus, or minus 8 equals 0, check. And similarly, 2, and then this is minus 12 plus 10 equals 0, check. So we have 2 comma negative 3. Now, if f of xy is equal to x minus 2y minus 8, and g of xy is equal to 1 plus, x plus 4y plus 10, then the derivative of f with respect to x, so here you treat y the same way you would treat the number like pi, for example. So it would be x, the derivative of that with respect to x is 1 minus 2 minus 8. There's that. And then f sub y would be the derivative of this with respect to y, so that's going to be negative 2. And then we've got g sub x is equal to, and these are actually constantly equal to, because when we differentiate them, they lose their variable nature. So g sub x is constantly equal to 1 plus nothing is 1. And g sub y is constantly equal to nothing plus 4 plus 10. Gonna just, or plus 0, I mean. It's going to be just 4, which means that the Jacobian at 2 comma negative 3 is going to equal 1, negative 2, 1, 4, which means then that the determinant of the Jacobian at 2 comma negative 3 is going to be 1 times 4 is 4 minus 1 times negative 2 is plus 2, so it's going to equal 6, it's not equal to 0, so check. It is indeed an isolated critical point. That's good. So then we need to figure out what the deal is with the eigenvalues and eigenvectors and such. So then, to find the eigenstuff, we have to use the matrix A, which is 1, negative 2, 1, 4, which then means that A minus lambda I would be 1 minus lambda, negative 2, 1, 4 minus lambda. And so then the determinant of a minus lambda I will be equal to, so it's going to be a lambda squared, it's going to be negative 4 minus 1 lambda is going to be total minus 5 lambda. 4 times 1 is going to be plus 4, minus negative 2 is going to be plus 2, lambda squared, minus 5 lambda, plus 6. Now then, if we have lambda squared minus 5 lambda plus 6 equals 0, then we would want to factor that if we could, and we can. So that would be lambda minus 2, lambda minus 3 equals 0, lambda equals 2 or 3. Both positive, distinct, real eigenvalues, which implies that what we were talking about is going to have two distinct eigenvectors, and they're both going to be attached to weights that are going to grow exponentially, and so that means it is going to be a proper nodal source. Sorry, improper. Improper nodal source, and what is actually going to make it improper is the fact that as it goes out of the origin, it's going to be riding along the trajectory of the eigenvector that will have the more significant weight when t is close to negative infinity, which is going to be this one. So whatever the eigenvector is for this one, it'll be pointing along that one. And then it'll be veering towards this one as t goes to infinity. Alright, so now let's try this again with something like this. So another example, let's try x prime is equal to x plus y minus 7, y prime is equal to 3x minus y minus 5. Now, first off, we have to try to find the equilibrium values. So that's going to be 0 equals x plus y minus 7. 0 equals 3x minus y minus 5. So it looks like I'd actually prefer probably to solve for y, so I can plug it into there. So y equals, looks like add 7, subtract x, so 7 minus x. 0 equals 3x minus 7 minus x minus 5. So that's going to be 3x plus x is 4x, minus x minus 5 is minus 12. Add 12 to both sides, divide by 4, and that looks like x is going to be 3. Put that in here, and that's going to give us y equals 4. Quick check on that. So 3 plus 4 minus 7 equals 0. 9 minus 4 minus 5 equals 0. Check. Okay. So we're talking about 3, 4. Now here, f is going to be x plus y minus 7. G is going to be 3x minus y minus 5. Which means that j, or I guess I should say, f sub x is going to be identically equal to just 1 plus 0 minus 0. F sub y is going to be 0 plus 1 minus 0, so it's going to be 1, identically. g sub x is going to be identically equal to 3 minus 0 minus 0. Oops, 3 I said. And then g sub y is going to identically be equal to nothing minus 1 minus 5. So they're equal to these numbers always, even at this value. Now, 3 comma 4 will then be same as any other point, 1, 1, 3, negative 1. And the determinant of that would be 1 times negative 1 is negative 1 minus 3 times 1 is, so that's equal to negative 4, which is not equal to 0. Check. And then it is up to us to find all the eigenstuff. So if the A here is going to be 1, 1, 3, negative 1, then A minus lambda I is going to equal 1 minus lambda I should say at the point in question, which so in the previous one, go back and say at what point, and it was at 2 comma negative 3. That was it for the previous one. So I was just confirm that. Okay, so then 3 negative 1 minus lambda. So then 1, 3, negative 1 minus lambda. The determinant of that, set that equal to 0, and solve for the lambda. This is going to give us the eigenvalues. So, what are we going to get here? It's going to be lambda squared. It's going to be plus lambda minus lambda, so nothing, and then minus 1. And then minus 3 equals 0, which means a lambda squared minus 4 equals 0, which means that lambda equals plus or minus 2, which gives us one positive, one negative. So it's going to be pointing inward along one trajectory, outward along the other, which means there will be a saddle point. Oops. Saddle point at, and it'll be at the xy values that we just found, 3 comma 4. So it'll be going inward along the eigenvector that corresponds to the negative, outward along the eigenvector that corresponds with the positive 2. Now let's try this with something a little bit trickier in that it is not directly written practically as a linear function, just with a little bit of a constant coefficient there. So now for example C, let's take x prime is equal to y minus 1. Y prime is equal to x squared minus y. Now, first off, in this context, what that means is that f is going to be y minus 1, g is going to be x squared minus 1. Now, let's figure out what there is to figure out. So, first off, if 0 equals y minus 1, then I already know that that means y equals 1. So there's that. And if 0 equals x squared minus 1, then that means x squared equals 1, which means x equals plus or minus 1. So that's going to give me two different critical numbers. It's going to be 1 1, and negative 1, 1. So there's that. Now, f sub x is going to come from taking the derivative of this function up here with respect to x. But there is no x involved there, so it's going to be 0 minus 0, 0. F sub y is going to be 1 minus 0 equals 1. And it's identically equal to that. G sub x. So now we're taking the derivative of something that involves the x, so it's going to be 2x minus 0. And g sub y is going to equal just 0. There's no y involved there, so it's just going to be identically equal to y to 0. Which means that j x comma y is going to be 0, 1, 2x, and 0. Now, the x values are going to be changing here. Sometimes it'll be 1, sometimes it'll be negative 1. So, we're going to have to break this up into two cases. So, first case for 1, 1. So, j sub 1, 1. Going to be what you get when you plug 1 in for x here. So it's going to be 0, 1, 2, 0. And the determinant of that is going to be 0 times 0 minus 1 times 2 which is not 0. So it's check. Okay, now if a is going to equal, so just calling it a for convenience really, and here we'll cut to the chase, a minus lambda I is going to be negative lambda 1, 2, negative lambda. So that's what we are talking about when we're taking the derivative and setting it equal to 0. So negative lambda 1, 2, negative lambda. Determinant of that equals 0. It's going to be lambda squared. And this is going to be minus 2 is equal to 0, which means that lambda is going to equal plus or minus the square root of 2. Which means that we are going to have a saddle point, because one is positive, one is negative. Saddle point at 1, 1. Now at negative 1, 1, we're going to have j, the Jacobian, which equals 0, 1, negative 2, 0. And the determinant of that is going to be negative 1, 1. Determinant is going to be 0 times 0, 0, plus 2 equals 2, which is not 0. Check. We always have to do this. This one's it's kind of a perfunctory check in most of these, but we just have to make sure that we're not talking about a critical point that is not isolated. Okay, so then when we do when we're going to find the eigen stuff, we have to go a minus lambda I, which is going to be this matrix here, be negative lambda 1 minus 2 minus 2, and then negative lambda. So very similar to the previous one, just with a negative 2 where there was a positive 2 before. And so then, take that, negative lambda 1, negative 2, negative lambda, and set that equal to 0, take the determinant lambda squared plus 2 equals 0, which means that lambda squared equals negative 2, which means that lambda equals root 2 times I plus minus. So we have a conjugate pair of purely imaginary eigenvalues. So this is going to be a center at negative 1, 1. So it's going to be stable, but not asymptotically stable. Because it does not approach any particular value, but neither does it diverge from that value. So it just goes into a stable orbit around that value. Alright, and now for last one here, let's take a case where we have x prime equals xy minus 2. So this is more similar to what we would see in, for example, the project, where it was not only not linear, but it had a term that was a multiplication of the two variables. And y prime, which equals x minus 2y. So then, just for reference, we can say f equals xy minus 2, g equals x minus 2y. That'll come in handy. Now, first to find the critical points, if 0 equals xy minus 2, and 0 equals x minus 2y, we can just basically do whatever appears natural to us here to solve one of the equations for one of the variables, and use that to get information from the second equation. So add 2y to both sides, and we'd have x equals 2y. And if we were to plug that in up here, that'd give us 0 equals 2y times y minus 2. So in other words, 2 equals 2y squared, which then the 2's would cancel. We'd have y squared equals 1, or y equals plus minus 1, which then implies that x would equal plus minus 2, and in particular, if y equals 1, x equals 2, and if y equals negative 1, x equals negative 2. So we're going to have 2, 1, and negative 2, negative 1. Alright, now take the derivative of f, the function f here with respect just to x, so treating y as though it is like the number 5. Well, if this had been the number 5 or pi or something like that, then what we're just going to end up with here is no x at all, just a y. And the derivative of f with respect to y is going to be, we take over here, treat the x like it's like a 3, and if we take the derivative, it would just be that 3. So in other words, it's just going to be that x. Now g sub x is going to equal the number 1, but it's going to be identically equal to that, so we must just hit. And g sub y is going to be identically equal to negative 2. Again, just because it's equal to a constant here, we want to make sure that we know that it is constant function, not just a one-off. So that means j of xy is equal to y x 1 negative 2. Now, starting with the 2, 1 problem, then what we're going to have is j of 2, 1 equals, so 1 for y, 2 for x, 1, 2, 1, negative 2. Now first confirm the determinant is not equal to 0. So that's equal to negative 2 minus 2, so negative 4, which is indeed not equal to 0. And then the other one, so then we will be doing a minus lambda I. Here is going to be 1 minus lambda 2, 1, negative 2 minus lambda. And so we are interested in the determinant of that. Setting it equal to 0 and seeing what we get. So when we take the determinant of this, we are going to be producing, by the look of it, a lambda squared. And then we'll have positive 2 lambda minus 1 lambda is going to be plus lambda. And then we're going to have minus 2, and then minus 2 is 0. So lambda squared plus lambda minus 4 equals 0. Now we're not going to be able to factor this, so we're going to have to go with the quadratic formula with a equals 1, b equals 1, c equals negative 4. And that's going to leave us with a lambda equals minus 1 plus minus square root of b squared minus 4ac, so it's going to be plus 16 divided by 2a is going to be plus 2. So the important thing here is that we're going to have negative 1/2 plus minus 1/2, or sorry, plus 1/2 square root of 17, and negative 1/2 minus 1/2 square root of 17. Now, I know the square root of 17 is some number. It's going to be a little bit above 4, which means it's going to be a little bit above 2, which means this one's going to be positive. This one's going to be negative, which means, since we have one positive and one negative eigenvalue, there's going to be a saddle point. Saddle point at, and choose this as 2, 1. And then at negative 2, negative 1, we will want to calculate the Jacobian. So negative 2, negative 1. So what was the Jacobian here? It was yx, so that's going to be negative 1, negative 2, 1, negative 2. So then the determinant of that Jacobian is going to be going to be 2 plus 2, which equals 4, which isn't 0, which is the important thing about it. Alright, now a minus lambda I is going to equal negative 1 minus lambda minus 2. 1 minus 2 minus lambda. And so, if we take the determinant, and set that equal to 0. So we multiply out, we're going to have a lambda squared, we're going to have plus 2 lambda, plus 1 lambda, is plus 3 lambda. We're going to have plus 2, plus 2, 0. And so we're going to have lambda squared plus 3 lambda plus 4 equals 0. And so we would factor this if we could. We can't though, so therefore we will use the quadratic formula with a equals 1, b equals 3, c equals 4, and then lambda equals minus 3 plus minus square root 9 minus 4ac, so it's going to be 16 divided by 2a, so that's going to be negative 3 halves plus minus 1 half square root of negative 7. So in other words, we're going to have negative 3 halves plus minus 1 half root 7i. And so the important thing here is that we have a pair of complex conjugate solutions with a negative real part. So the complex solutions mean we have something circular-ish, but if the real part is positive, that would have meant a spiral outward. If the real part is negative, that means a spiral inward. So we've got a spiral sink. And that was at negative 2, negative 1. Alright, so that's what these things will all end up looking like. But let's take a look at each of them in turn on Bluffton and see how they look. So before going to Bluffton, let's just summarize our examples. A summary of examples. A, which had the system x prime equals x minus 2y minus 8 and y prime equals x plus 4y plus 10. So this one had a we discovered that it had an improper nodal source at 2, negative 3. And leave some space here. We'll check whether it is confirmed or not at on Bluffton. So then x prime, so b was x prime equals x plus y minus 7. Y prime was equal to 3x minus y minus 5. And our conclusion on that one was a saddle point. At 3, 4. C, what we had was x prime equals y minus 1. Y prime is equal to x squared minus 1. And so that gave us a saddle point at 1, 1. center at -1, 1. And then D, x prime is xy minus 2, y prime is x minus 2y. And our conclusion there was that there was a saddle point at 2, 1 and a center at, sorry, a spiral sink. Wrong thing I was reading. Spiral sink at -2, -1. So now let's confirm this all with Bluffton. Quick correction, I just wanted to point out, there was a typo up there. It was I wrote +0 at first. It should be +10, +10, +10. Okay, now to look at the Bluffton. Alright, so what I got up here now is dual screen, where we can see on the right what we summarized as the consequences of our actions, and on the left we're going to bring up Bluffton. So let me put that out of the way for a moment. Alright, so for the very first system, system A, what we had was, well, x prime equals x minus 2y minus 8. So x prime equals x minus 2y minus 8. For the y, what we had was x plus 4y plus 10. Okay, and let me bring this out a little bit bigger. Might as well make it nice and big. Alright, and then I'm expecting there to be an improper nodal source at 2, -3, so I'll make my y window a little bit bigger to allow me to see it better. And what you will see here in Bluffton is indeed a source. Now, this may look a lot like a spiral point, and the naked eye can be a little hard to tell exactly sometimes, but technically this is an improper nodal source, and if you look, all of the solutions end up going parallel to like this direction, so this would be one of the eigenvectors. And then as they get in closer to the equilibrium, they are all going like this way, which is the other eigenvector. So an improper nodal source at 2, 3. Check. Now let's try the second one. So we are expecting to see a saddle point at 3, 4 if the differential equation matches differential equation B. So for equation B, my x prime should equal x plus y minus 7. My y prime should be 3x minus y minus 5. Alright, and let me clear all my curves because they're all now based on irrelevant points, and it looks like a saddle point at 3, 4, so I guess I'll want my y values here. I'll make this go -3 to +5, so that way I can include that point. Alright, and now let's have a look. So when we put that out of the way, we are expecting to see at 3, 4 a saddle point. Is that what we see? Well, sure enough, it's doing what a saddle point does, approaching it from the vector going this way and receding from it in the vector going that way. So this is classic saddle point behavior. So we have another confirmation. Alright, now let's try example C. See how that one plays out. We have x prime equals y minus 1. We have y prime equals x squared minus 1. And now we are expecting to see a saddle point at 1, 1, a center at negative 1, 1. So let's just change our window to go negative 2 to 2. And let's go 0 to 2 on the y, just to give us full resolution here. Alright, and now let's have a look. So at the point where we had, well, we're supposed to have a saddle point here, we can see it's doing saddle point stuff. It's going around in all kinds of saddle pointy ways, going towards in one direction, away from in the other. Classic saddle point behavior. As for the center, we are expecting to see something that is going around and around. Now, you may have expected that it would be a more stable orbit than this. However, depending on the method that you use, it may not actually come out as stable as it should. So notice under Euler method, it ended up spiraling outward. That's because of Euler's errors. But the Runge-Kutta method is able to display better the actual stable but not asymptotically stable nature of this. So a better approximation method can make things show up a little bit better than they otherwise would. Notice, by the way, we can, if we get out far enough on these, we can get it to go even over to that part, which is cool. Alright, clear all the curves, and sure enough, we have confirmation on both of these. Check and check. And then the last one we're going to look at is the one that was D, where we had an x prime of x times y minus 2 and a y prime that was x minus 2y. Now what we're expecting to see here is a saddle point at 2, 1 and a spiral sink at negative 2, negative 1, so it looks like x value should go from like negative 3 to 3. And y value should go from, let's say, negative 2 to 2. Alright, now let's have a look. So we are expecting a saddle point at 2, 1, sure enough. There it goes, being a saddle point. And we're expecting a spiral sink at negative 2, negative 1, and there it goes, being a spiral sink. So sure enough, we have once again Bluffton approved confirmation of this and this. So on that note, let's call it a section. I'll see you next time for the next episode of Math 256. Till then, bye.